Greetings, Gen Chem 1007 students. This is going to be the end of chapter 8 and very important stuff. There are exceptions to the octet rule, and we're going to find out reasons why. There are, like, we're going to find out that some molecules have odd number of electrons. We haven't seen that yet. We're going to see that some ions or molecules will have less than an octet. They won't obey the octet or 8 electron rule. And then we're going to see molecules that have more than 8 valence electrons and they have an expanded octet, and you can imagine they involve d orbitals. And so here's a very interesting molecule, very important. Um, it's actually pretty unstable. It's also biologically nitrogen oxide. Um, we'll find out nitric oxide, they often call it. And nitric oxide, for example, causes blood vessels to dilate. It's very important in physiology and to keep blood flow and to keep people from having heart attacks and to get blood to proper tissue. And so we have an odd electron arrangement where there's not enough electrons to create these lone pairs, and we end up with a almost like a radical like situation, which is usually very unstable because radicals, single electrons, always want to pair up, so they will react with almost anything around them. So we could have the electron here on the nitrogen, or we could have the electron here on the oxygen. We can actually get both. Both species are possible, although we can look at the valency of each atom individually. Nitrogen has 5 valence electrons, oxygen has 6, for a total of 11 electrons. We have no charge, so we can't add another electron. We have to take it for exactly what it says, and it's 11 electrons. If we had a negative charge on this, it would have 12 electrons, and we would lose the radical. So a single electron is a radical. That is a radical, right? That is a radical. That is a radical, very reactive, and if it's nitric oxide we're talking about, it has a biological effect. And so we see that with nitrogen oxide. So what else? Looking at 8 valence electrons, we have a case where sometimes it's a bad idea to have 8 electrons around an atom, and we go back to what we just learned about formal charges. So if we do, we see that boron only has 6 electrons, and it, like just like carbon, it should have 8. It has 3 valence electrons. It needs 5 to fill its valency. Fluorine needs 8 to meet the octet rule. It has 7 typically. So if we pair everything up and we pull this in here, and we're able to do that, we create a double bond there, and we do meet the octet rule. But this doesn't happen. None of this happens. None of this is going to happen. It's going to stay like this, and it's going to violate the octet rule because of energetics, because it won't put formal charges on boron. It won't put a positive charge on fluorine and a negative charge on boron, which is the very opposite. Fluorine doesn't want a negative charge. It's very electronegative. Or excuse me, fluorine does not want a positive charge on it. It's very electronegative. It wants to be negative, and it does not want to receive a positive charge for anything. It's very destabilizing. So if we do this, we're going to put a positive charge on fluorine, and that's really bad. We don't want to put a positive charge on fluorine at all. It'll also put a negative charge on boron, and the boron is not highly electronegative. So if we were to calculate this and say that we did do this, and we did, this is the correct. We don't want to do this, but if you did make the mistake of doing this, you could do the formal charge on fluorine, where you have the double bond, and you would say to yourself, this would become a double bond, right? This would become a double bond. And if you did that, let's evaluate boron first. Boron has 3 valence electrons, but if it's got a sigma electron a pair and a pi electron pair, it has 4 electrons, and so it has no it has no lone pairs of electrons, so we can rule that out. But now it has 1, 2, 3, 4, 8 electrons that it shares. So we say 1/2 of those 8 electrons. So it's kind of just like carbon, right? So it's kind of just like carbon. And we end up with 4 minus 3. We put a negative charge on boron. We put a negative charge on boron. If we did this for fluorine, let's see what kind of formal charge. We're doing formal charge calculations. So again, for formal charge calculations, we need the valence electron that each atom has from the periodic table, which is 7 for 7 is the number for fluorine. And we see that we have a double bond here. We have a sigma bond, and we have a sigma bond, and then we have a pi bond, right? This is a sigma bond, a sigma bond. Let me see if I can draw that. And then that is a pi bond, which is high energy. And if that's the case, then fluorine will have moved. It doesn't have these lone pairs to itself anymore. But if we figure out, how many electrons belong to fluorine completely, that's 4, 2 lone pairs. So that's now 4 because we move 2 electrons in to form a pi bond with a sigma bond. So we have a double bond between fluorine and boron where they share electrons. Now we have to calculate how many electrons are shared and give half the value to fluorine as well. We see that fluorine now has 1, 2 pairs of electrons that are shared, so that's 4 electrons. So 4 electrons, and so now we have this 4 minus 2, excuse me, that's not a minus, 4 plus 2 is 6 electrons. So a fluorine, if that's the case, we have 4. Let me double check this. 2, 4, half of the electrons, we have 7. And doing that, we get, we've got looks like a 2, 3, 4, and we're going to end up getting a positive. We're going to get a positive. We're going to be shy an electron. We need 7. We're only going to have 6. And so we're going to end up having a +1 for this. We're going to end up having a +1 for this. And because we have 7 electrons that we need, we're only going to have 6. Fluorine's going to end up having a +1, and that's not good. We don't want that. So now we're going to have to figure something out. We will have a plus charge on fluorine, and we don't want that. So we do not want to pair up these electrons. We want to violate the octet rule in this case. We don't want to follow the octet rule in this regard. We get a +1 when we do this. We get a +1, and so we're shy an electron that we need, and we get a +1 charge on that fluorine. We luckily got a -1 here when we did this calculation. So be careful. We're shy an electron. We got a +1 charge. We have another case where 8 of valence electrons is not enough. We actually need to have more valence electrons surrounding phosphorus. We're going to end up pairing one of these. We're going to end up pairing just one of these, and it's going to end up getting rid of these. It's going to get rid of the additional formal charges. So we're going to end up getting a double bond and removing this here. And although we're still going to have a -3 formal charge on the entire molecule, we will will have eliminated the phosphorus will no longer have a +1. It'll become 0, and this will become 0 by just pairing that up. So we'll end up we'll still have the same charge, but all the negative charges will be on oxygen. We won't put anything on phosphorus, and we will have less charges overall. So even though the charge remains the same, when we change this, we eliminate the -1 and the +1 on phosphorus to give us a 0 and 0 by pairing up, by bringing a lone pair in here to form a pi bond and making a double bond. And so we have a double bond between oxygen and phosphorus, and we get rid of the charge distribution. And so that works out nice. We have less charges on on atoms. So instead of having all 5 atoms with some kind of charge, only 3 of them will have a formal charge, and it's all on oxygen with a -1. Review that if you don't understand that, come see me, but we're going to end up with 10 electrons around phosphorus, so it's going to have more electrons than it needs. It's going to break the octet rule by having more electrons. It's going to have 10 instead of 8. So they call that hypervalent, and that means because of d orbitals, it can take on more than an octet. Doesn't happen all the time, but it happens often enough. This is a very phosphorus, phosphate. Phosphate is what we draw, is very prevalent in biology, part of ATP. It's a very high energy bond, by the way. Now we can look at single and multiple bonds. Enthalpy can be done in so many ways. We only touched a little bit on bond enthalpy. If you take physical chemistry or more thermodynamics, you'll learn that enthalpy can be calculated in many, many different ways. There are many ways to calculate enthalpy. Remember, enthalpy is a state function. It doesn't matter the path that you take, it just matters what the enthalpy equals in the end, whether it's negative or positive, and which direction are you going. Are you putting in energy to turn it into a gas, or are you taking out energy to turn a gas into a solid? But this is another way to do enthalpy. This is one of many, many ways. Heat scientists, energy scientists, this is a simple way to do enthalpy. Why do enthalpy the real complicated way and heats of formation and all these other crazy things, when what you can do is simply take bond breakage. If you break this bond, if you break that bond, it costs 413 kilojoules per mole. Positive. If you form this bond, if you would form this bond, it would be negative 413 kilojoules per mole by reforming the bond. The same thing if you break this carbon bond, it's going to be positive, right? But if you form the carbon bond, it's going to be negative. Whenever the bonds form, energy is given off. Whenever the bond is broken, it takes energy to break it, and it releases energy when it forms. Okay, so bond breakage, if I'm going to put BB for bond breakage is always a negative, always equals a negative value to break a bond. But then you can reform a bond, and you can bond formation, we'll call that bond formation. And that is always positive. Bond formation is always positive. So if a fluorine bond forms, it's going to be bond breakage. Oh, I've got this wrong. Bond breakage is positive. Oh, bond breakage is positive. You have to put in energy to break a bond. And bond formation is negative. It's negative. If you form a bond, it has to have a reason to form, and therefore it's going to be exothermic, and it's going to be negative. That's never going to change. Bond formation is always negative, and bond breakage is always positive. You put in energy to break the bond, which is going to be positive enthalpy. When another bond forms, you're going to have a bond formation, and that's going to release energy, and it's going to be exothermic. Okay, so if carbon and nitrogen, you want to break that bond. If you break that bond, that's going to be positive. If you reform it, it's going to be negative. If you break the carbon oxygen bond, it's going to cost you plus 358 to break that bond. If you form a carbon oxygen bond, it's going to end up being a negative, and it's going to release 358 kilojoules per mole when it reforms. It only works one direction. Make sure that makes sense, right? So if you were to break a carbon-carbon bond, so you broke one carbon-carbon bond, you're going to break that bond, and that gets broken in half. That is going to equal, to break that bond is going to be positive 348 kilojoules per mole, right? 348. Remember the units. And say now you break one carbon bond, and then you form This is bond breakage, BB, so it's going to be it's going to be positive to break those bonds. It's going to be positive to break those bonds. It's going to cost 348 uh, kilojoules per mole to break those bonds. But for bond formation, it's going to be exothermic, and um, it's going to be negative. So you broke a carbon-carbon bond. You had to put in 348 kilojoules per mole. So it cost you the energy that you had to put into that chemical system per mole was 348 kilojoules to break that carbon-carbon bond. Now, say you're going to have a bond formation where you make two carbon-hydrogen bonds. So each carbon here, that there's one bond breakage, but now you're going to add a carbon and a hydrogen and a carbon and a hydrogen. So you're going to have what amounts to two carbon hydrogen bonds forming. So you're going to have a carbon and a hydrogen bond forming here, and you're going to have two of those. And now it's going to be exothermic, it's going to be negative. And you see, you go to the table, it's 413 kilojoules per mole to break that bond. But to form it, it's the opposite. It's going to be a negative. So it's going to be 2 times negative 413 kilojoules, and we'll forget the units for now. It's always in per mole. So that's going to be 826, and it's going to be a negative 826. And so all you have to do is you add 348, right? 348 minus 826, right? So you're going to end up with a number such as you're going to have a negative number, and it's going to be roughly, when we figure this out, something like 22. It's going to be 522, 522, negative 522 kilojoules for the overall reaction. So how does that work again? We broke the carbon-carbon bond. There's only one of those, so that's a plus 348 kilojoules of energy we had to put in to break that bond. And then we reformed, we had bond formation where a carbon and a hydrogen bond are formed, and there's two of those that form. So we have 2 minus 413 kilojoules per mole, giving us 826. We go over here, we take 348 and we add that to a negative 826. And we know that that overall chemical reaction is exothermic and costs us negative energy. We release energy in that reaction, and which makes sense because when we break a hydrocarbon such as octane or butane, we release a lot of energy. So a lot of energy is released in that reaction, a negative 522 kilojoules per mole, in breaking one carbon-carbon bond and forming two carbon-hydrogen bonds. And we have an exothermic reaction, which is what combustion is. That's like a combustion reaction. Notice the enthalpy of bonds are different. They're not all the same. And in fact, there's a trend we're going to find out. What we see some of these other bonds, like with silicon and carbon and sulfur bonds and sulfur and bromine, they're kind of like in the same range of what we just saw with these other single sigma bonds. These are all sigma bonds. When there's single bonds, there's sigma bonds, right? That's a sigma bond. That's a sigma bond. It's a single bond. But when we have double bonds, the energy goes up. Double bonds have a sigma bond and a pi bond, right? We have a sigma bond, and which is lower energy and harder to break, and we have a pi bond, which is high energy and more reactive. And so the energy goes up for double bonds, as you would expect. It takes more energy to break a double bond than a single bond. We have to break a sigma bond, and we have to break a pi bond to separate the carbon-carbon atoms. And to break it takes a plus 614 to break that bond. If it were to reform, it would be a negative, right? So bond formation would be a negative. Bond breakage is always positive. To break a nitrogen double bond, it's going to be plus 418 kilojoules to break that bond in half. But if we were to reform it, it would be a negative. And so we could do this so on and so on. And this is another way to do enthalpy easier than doing, for example, Hess's law and doing all these complicated calculations. Enthalpy is only dependent on the overall value. It's a state function. The path does not matter. Although we looked at lattice energy and we could see all these steps, and the steps are, of course, the path. But the enthalpy values, we can get those any way we can find them, and sometimes simpler is better. So learning all these enthalpy tricks, especially if you're into solar science and heat science and energy and even maybe rocket science, you're going to need stuff like this eventually. So we can plot bond enthalpy versus bond length, and the bond enthalpy is the y value. It's the y on the y-axis, and bond length is on the x-axis. And so we can take a nitrogen, a triple bond nitrogen, a triple bonded nitrogen, and it has the most energy to break it necessary, almost 1,000 kilojoules per mole to break those three bonds. You have two pi bonds and a sigma bond, right? So this consists of, just in case you didn't know, a sigma bond, which is always a single bond, but then it has two pi bonds, and then a pi bond, another pi bond. So it has two pi bonds and a sigma bond. So it takes a lot of energy to break that. If we only have a double bond, we have what? We have a sigma bond, which is usually longer, but then a pi bond, which is more high energy. And that takes more energy to break than, say, a single bond over here, which is the lowest on here, which is only a sigma bond, which takes the least amount of energy. Now, the closeness, the length of the bond is important. The length of the bond, it's much shorter. The nitrogen triple bond is very short compared to the nitrogen-nitrogen bond, which is longer. And as you would expect, the double bond is right in between the single bond and the triple bond. So the longer and longer these bonds get spread out, the easier they are to break. They're already being stretched. And as they get longer and longer, the two atoms get further apart and you get bond breakage. So that does it for chapter 8. I'm glad you bared with me. Add your own things to this. Ask me questions. Get help if you don't understand this. And I will see you in class, dear Chemistry 1007 students. We are finished with chapter 8. Congratulations.